the most produced U.S. carrier-based attack aircraft, which dutifully went through the fire of Vietnam and Iraq, yet managed to remain practically unknown to the general public. While other aircraft bask in the glory, this humble worker of the aircraft carriers rolled off the assembly line in Dallas every single day to become the most accurate and effective subsonic bomber of its time. Friends, meet the undeservedly forgotten carrier-based attack aircraft, the A-7 Corsair II. How did this machine manage to perform loops and barrel rolls with 12 heavy bombs on its hardpoints right during demonstration flights? Why did the factory in Dallas produce one brand new Corsair every single day for several years, working at the limit of its capacity? And what dangerous defects with the brakes on wet carrier decks did engineers have to rush to fix right in the middle of the war? Now we will analyze the hidden tactical features of this machine and tell you how the Corsair's targeting computer made a real revolution in the accuracy of airstrikes. Let's begin. The deck trembles. The engine roars so hard it feels like it is about to tear itself apart from the inside. The pilot keeps his eyes on the white line ahead, to the edge of the deck, less than 80 meters. In 4 seconds, the wheels will either lift off the metal or they won't. This is not a test range in the middle of a desert. This is an ordinary working day aboard a United States Navy aircraft carrier. Such a takeoff is repeated here dozens of times per shift, and almost no outsiders know about it. By the mid-1960s, U.S. carrier aviation encountered a hitch that could not be resolved for almost 5 years. The Navy's primary attack aircraft was outdated, and a replacement could not be found. We are talking about the A-4 Skyhawk from Douglas, a small, nimble plane, but one that no longer met the requirements of modern combat operations. Its flight range was modest and its payload was limited, while the tasks facing the Navy were becoming increasingly complex. It would seem simple: build a new plane and the issue is resolved. But in reality, things turned out to be much trickier. It was a matter of money and time. Designing a combat aircraft from scratch means years of engineering work and colossal budgets, and the U.S. Navy in the mid-1960s needed a new attack aircraft here and now, not 10 years down the road. And this is where the truly interesting part of the story begins, because the decision the engineers ultimately made went against everything that was considered correct in combat aviation at the time. Instead of chasing speed and creating yet another supersonic fighter, Navy officials bet on something completely opposite. It was this choice that determined the fate of the machine for its next nearly 30 years of service. Today, such a decision seems logical. Back then, in the midst of the speed race, it looked almost insane. A bit later, you will understand why a slower aircraft turned out to be smarter than a fast one. But for now, let us return to where it all began, to a small working group tasked with solving a problem that seemed unsolvable. By the mid-1960s, the Navy command faced a task for which there was no ready solution. Building a new plane at random was too expensive. Making a mistake in the calculations was too dangerous for the entire carrier aviation program. So they took an unusual approach. Instead of immediately announcing a competition for a new attack aircraft, they created a small working group of specialists. Its task sounded dry and businesslike: to determine which flight characteristics a prospective carrier-based aircraft needed first and foremost. Engineers and analysts sat down to do the calculations: speed, range, payload, production cost per machine, and the time required for construction. Every parameter was analyzed, compared, and debated for weeks. And here begins a truly unexpected turn. Based on the results of their work, the group reached a conclusion that went against almost all the trends of that era. Now picture the whole situation. It is the height of the speed race. Design bureaus around the world are competing to see who can break the sound barrier faster. Fighters are becoming sleeker, faster, and more expensive with each passing year. And suddenly, this group of specialists declares the opposite. A subsonic aircraft would be more cost-effective than a supersonic one. It would be more compact, cheaper to produce, and, crucially at that moment, it could be built significantly faster. Sounds like a step backward, doesn't it? But in reality, it was a cold engineering calculation, not a retreat. The fact was, a carrier-based attack aircraft did not need to exceed the speed of sound at all. It needed to stay in the air for a long time, carry enough bomb load, and accurately hit its targets. Speed, in this specific task, was far from the top priority. Moreover, a simpler, slower machine meant fewer design risks. and fewer risks meant less time spent on testing, times that, as we recall, the Navy was running out of. The working group's conclusion landed on the command's desk and literally turned the entire future plan 180 degrees. Instead of another high-speed fighter, the Navy decided to order something much more modest on paper and much more practical in real service. Thus was born the procurement program for a new light attack aircraft for carrier aviation. The program received the green light, but it came with one condition, a condition so strict that it immediately cut off most of the possible development paths for the project. The condition sounded almost insultingly simple to the engineers. No new designs from scratch, only what is already on the production lines. Imagine a design bureau where people have spent years dreaming of creating something revolutionary, and then they are told, forget about the blank slate, take what is already flying and modify it. This is exactly how the main requirement of the new procurement program was formulated: maximum cost reduction of the new machine's production at all costs. This meant that the development of the new attack aircraft required using existing airframes already in production. The logic behind this was ironclad. Designing a completely new aircraft from scratch takes years. It requires huge investments and constantly risks failing at any stage of testing. Modifying an already proven and flying aircraft, however, cuts both time and expenses several times over. The Navy, in essence, said one simple thing to the nation's designers: we don't need a revolution. We need results, fast and cheap. For some companies, this condition was almost a death sentence. Their ambitious designs for new aircraft instantly lost all meaning. Why draw a dream plane if the customer is directly asking you to take something ready-made? But for others, this condition, on the contrary, opened a door. And this is where Vought, a company belonging to the LTV Industrial Group, stepped onto the stage. Unlike its competitors, they did not argue with the program requirements. The company's specialists took the recommendation literally and did not try to bypass it with clever tricks. If a ready-made airframe was needed, then a ready-made airframe is what they would deliver. Admittedly, it sounds like a compromise rather than a bold engineering solution. But as you will see later, this very constraint forced the designers to find an unexpectedly elegant path. Meanwhile, something greater than just an aircraft delivery contract was at stake. A real battle erupted among several of the country's largest aircraft manufacturers for the right to fulfill this condition, and not all of them were destined to emerge victorious. The program received its official name, the procurement of a new light attack aircraft for carrier aviation, and almost immediately a real struggle began for the right to secure this contract. 4 major aircraft manufacturing companies in the country entered the competition: Douglas, Grumman, North American, and Vought, which was part of the LTV Industrial Group. Each of these companies had decades of experience behind them. Each had already built successful combat aircraft for the Navy, and each was confident that its design would prove to be the best. Imagine closed meetings in 4 different cities across the country, drafting tables piled high with blueprints, engineers arguing until they are hoarse, choosing which of the existing airframes would best suit the Navy's requirements. "We have a ready-made platform," says one company representative at a design defense meeting. "So do we," replies another at a nearby meeting, hundreds of kilometers away from the first. The requirement was the same for everyone: take an existing production airframe and modify it for the new task. No clean sheet development from scratch. And this is where the most interesting part begins, because each company approached this requirement in its own way. Some proposed minimal modifications. Others, on the contrary, wanted to alter the aircraft almost beyond recognition, risking exceeding the budget and deadlines. The competition turned into a delicate balance between boldness and practicality. The Navy Commission studied each project for months. They compared the estimated production costs, examined the projected flight characteristics, and evaluated how quickly each company could set up mass production. Now here is a question that should have been asked of any of the 4 contenders at that moment. What is more important, to create something technically flawless, or to give the Navy a working aircraft as quickly as possible? Vought placed its bet on the second option. And this bet turned out to be unexpectedly accurate. The winning solution amazed many with its simplicity. Instead of complex new designs, the company's specialists proposed taking a carrier-based fighter that had already proven itself excellently and turning it into something completely different. The competition ended and the winner was announced. But to understand just how bold this decision actually was, one must look at what was hidden beneath the skin of the new attack aircraft. As the basis for the new attack aircraft, Vought chose a plane they already knew inside out and knew how to build, the F-8 Crusader carrier-based fighter. It was a machine proven by time and combat service, fast, maneuverable, and reliable. But the Navy did not need a fighter at all. The Navy needed an attack aircraft capable of carrying mini bombs and accurately hitting ground targets. Therefore, the engineers took the existing airframe and began, in essence, a surgical operation to change its inner nature. The first thing that catches the eye when comparing the two aircraft is the length. The fuselage of the new aircraft was noticeably shortened compared to the donor fighter. Less length meant less weight and more maneuverability at low speeds, which is exactly what an attack aircraft needs when rolling in on a target. Next is the nose of the aircraft. On the F-8 Crusader fighter, it was sharp and elongated, designed for high-speed flight. On the new attack aircraft, the nose cone was rounded. This shape was better suited for housing the new avionics and did not require the aerodynamics needed for supersonic fighters. And finally, the wing. The engineers installed a wing with less sweep than that of its fighter predecessor. This sounds like a technical detail for specialists, but in reality, this decision directly affected everything: handling at low speeds, range, and the ability to carry a heavy bomb load. Imagine a sports car that had its body shortened, its hood shape changed, and its suspension replaced for a completely different task. Externally, it is still a recognizable machine, but in essence and purpose, it is already something else entirely. This is exactly what Vought's engineers did with the Crusader fighter. The resulting aircraft retained the proven structural design of the airframe and the general layout, but became a completely different machine in terms of its purpose and flight characteristics. But was it worth radically modifying a ready-made fighter for the role of an attack aircraft? The answer to this question was provided not by theory, but by the first flight of the new machine. Only one thing remained to be seen: would this conversion fly as intended on paper? And would the new attack aircraft manage to prove that a subsonic plane could indeed be as good as, if not better than, its high-speed rivals? Early morning. The airfield is shrouded in a light haze. Engineers and Navy representatives stand slightly to the side, arms crossed, barely breathing. On September 27, 1965, the new attack aircraft takes to the air for the first time. The engine roars, accelerating the machine down the runway. Another second, and the wheels lift off the concrete. Everyone standing below looks up in unison. The first flight of any combat aircraft is a moment of truth. Calculations and blueprints will not help here. Either the machine flies as intended, or years of work go down the drain. The test pilot takes the attack aircraft higher and enters the first turn. Down on the ground, one of the engineers quietly exhales. But the real test was still ahead. It was one thing to just take off, and quite another to prove that the new machine could handle the task for which it was created. A few weeks later, the pilots performed a stunt that made the Navy Commission look on in disbelief. Under the wings and fuselage of the attack aircraft, they hung 12 250-pound bombs, which is just over 113 kilograms each. With such a load, most combat aircraft of that era struggled to perform even basic maneuvers. Yet this aircraft, with a full payload, performed a complete barrel roll in the air. Imagine a truck fully loaded with cement sacks that suddenly and easily executes a sharp turn at full speed. This is roughly what the demonstration looked like to those watching from the ground. The Commission appreciated more than just the spectacle of the maneuver. They valued what stood behind it: the immense structural strength of the design and the amazing stability of the aircraft, even with a maximum combat load. And the numbers spoke for themselves. In terms of maximum combat load, the new attack aircraft was twice as capable as the A-4 Skyhawk it was designed to replace. Twice. Think about that number. Not 10% more, not a third more, but literally double. For the Navy, this meant one thing: a single mission of the new attack aircraft could now replace 2 missions of the old machine. Less risk for the pilots, lower costs, and greater efficiency. The tests were successful. The airframe, assembled on the basis of an existing fighter, fully confirmed all the calculations of the working group. But it is one thing to prove oneself on a test range, and quite another to organize the production of thousands of such machines in tight time frames. Almost immediately after the first successful flights, a race of a completely different kind began, the production race. Dallas, Texas. A massive hangar stretches for hundreds of meters, flooded with the bright light of lamps. The clatter of metal, the hiss of welding machines, and the hum of conveyor belts do not stop for a single minute. 35,000 people work at the Vought factory. It is as if the entire population of a small town came here every day to assemble a single aircraft. And not in a week, not in a month. Every single day, one brand new attack aircraft rolled off this assembly line. Imagine a conveyor belt operating so harmoniously that in 24 hours, it manages to go from individual metal parts to a fully completed combat aircraft capable of taking to the air. And so it went, day after day, for several years in a row. A shop foreman walks along the line and stops at another fuselage. "Is wing number 8 ready?" "We are finishing the fastening," a worker replies without looking up from his tool. "We have 6 hours, no more." Such conversations were heard here constantly. The pace of production left no room for delay. Every part, every assembly, and every rivet had to fall into place exactly on time. Now imagine the scale of it all. Over the years of production, from 1965 to 1984, 1,569 of these attack aircraft were built. 1,569 aircraft. This is not just an impressive number, it is proof that we are looking at a truly successful and in-demand design, rather than a stroke of random luck. After all, if the aircraft had disappointed the customer, production would have been wrapped up quickly to find an alternative. Instead, the line operated for years, without stopping, meeting the needs of the United States Navy's carrier aviation. Every such attack aircraft, upon leaving the conveyor belt, headed to the exact same destination, to the decks of aircraft carriers, to those who would fly them. And this is where, perhaps, the most honest part of this story begins. Because it is one thing what engineers and factory inspectors think of an aircraft, and quite another what those who climb into the cockpit and take it into the sky every day have to say. The real evaluation of any combat aircraft is given not by engineers or factory inspectors. It is given by those who climb into the cockpit every morning and trust this machine with their work and their safety. In the Navy, the new attack aircraft was received surprisingly warmly. Word quickly spread among active-duty pilots. Handling this machine turned out to be noticeably easier than many other carrier-based aircraft of the time. The pilot climbs into the cockpit. The instrument panel in front of his eyes is clean and clear, without unnecessary toggle switches to catch his eye at the most inconvenient moment of landing. "How does she handle?" a young pilot asks someone who has already flown dozens of hours in the new attack aircraft. "Like a good tool. It does exactly what you expect of it, nothing extra." It was this simplicity that won the pilots over most of all. No unnecessary temperamental behavior, no unexpected surprises during normal flight. But pilots particularly highlighted one detail: forward and downward visibility. For an attack aircraft, this is perhaps the most important operational quality of all. What is the use of the most modern avionics on board if the pilot simply cannot see the target behind the long nose of his own plane? Here, the designers solved this problem as well, by shortening the fuselage of the donor fighter. This is somewhat similar to the story of cars that finally had the blind spot near the windshield A-pillars removed. It seems like a minor detail on paper, but it is what determines whether you make the turn or not. The pilots reported practically the same thing to command. The machine is simple, responsive, and provides excellent visibility during a combat run. Many even admitted that after switching to the new attack aircraft, they did not want to go back to their previous equipment. It would seem like an ideal picture. Everyone who flies the aircraft loves it. But any piece of equipment reveals its true character not in calm flying weather, but in difficult conditions. And that is exactly where several unpleasant traits of the new attack aircraft came to light. Rain drums against the canopy. The runway ahead shines like a dark mirror. The pilot grips the controls tighter, knowing that it is in this kind of weather that the new attack aircraft shows its less agreeable side. The first months of operation revealed several problems at once, and they all manifested themselves precisely when conditions ceased to be ideal. The first problem was stability when landing in a crosswind. As soon as the wind blew from the side, the machine began to behave noticeably less predictably than pilots would like on a short carrier deck. The second problem was just as unpleasant. On a wet runway, the attack aircraft's braking performance was poor. And for a machine landing on a pitching deck in the open sea, this was far from a minor issue. The runway is flooded. The stopping distance is slipping, a pilot reports after another landing. Write it down in the report. The engineers need to see this. And the third problem concerned the very heart of the machine. The new attack aircraft was noticeably lacking in engine thrust. With a full combat load, the aircraft accelerated and climbed significantly slower than desired in a real combat environment. 3 problems and 3 different solutions. The engineers managed to deal with the first 2 relatively quickly. The braking issue was eliminated by modifying the design of the braking system itself. Pilots no longer had to fear rain before landing. But the lack of thrust could not be resolved so easily. A minor modification was not going to cut it here. And so, a decision was made that sounds both simple and radical. The weak engine was replaced with a more powerful one, the Pratt & Whitney TF30-8. Imagine a car where, instead of cosmetic tuning, the entire engine is replaced with a more powerful unit under the same hood. This is roughly what was done with the new attack aircraft. Thrust increased noticeably right away. The aircraft, with a full combat load, now climbed exactly as had been required from the very beginning. The 3 weak points were eliminated one after another. And only after this did the attack aircraft truly reveal what made it special among other combat aircraft of its time. The cockpit is cramped. The instrument panel flashes with dozens of indicators. The pilot looks at a small screen in front of him and sees something that pilots of the previous generation of aircraft had never seen. By the end of the 1960s, the new attack aircraft received something that seemed almost like science fiction at the time: an onboard digital targeting computer system. Imagine the difference. Previously, a pilot aimed almost by eye, relying on his own experience and intuition. Now, electronics onboard the aircraft took over part of the calculations. The computer took into account the machine's speed, altitude, dive angle, and even the airflow conditions at the moment of release. It then provided the pilot with a precise point on the display to hit, ensuring the bomb landed exactly where it was supposed to. How much of a difference did this make? The difference was immense. Before the advent of such systems, the spread of hits was measured in dozens and sometimes hundreds of meters. With the new targeting system, the attack aircraft began to strike targets with an accuracy that seemed impossible to many for a machine of its class. "First run," the pilot reports over the radio. "Roger that. We observe a hit exactly in the square." "From the first run?" "Affirmative. From the first." Reports like these quickly became a regular occurrence rather than a rare exception. This is like an ordinary family car today suddenly receiving an autopilot system that was previously only installed on high-end luxury models. The leap in capabilities was felt just as sharply. In addition to accuracy, there was another major advantage: a long flight range. The attack aircraft could fly further than many other carrier-based aircraft of its time, meaning it could reach targets located deep beyond the range of its competitors. Range plus accuracy plus a solid combat load, it was this combination that turned a modest subsonic aircraft into one of the most effective carrier aviation tools of its generation. But any technical achievements are tested not on a range or in committee reports. They are tested where the price of a mistake becomes truly high. The tests were over. The production lines in Dallas were working at full capacity. And very soon, the new attack aircraft was to apply all its capabilities not on a test range, but in real conditions. The first serious test for the aircraft was combat operations in Southeast Asia. It was there, in a difficult climate and over heavily defended territory, that the attack aircraft first showed what it was truly capable of. Pilots noted the exact qualities that were designed into the aircraft from the very beginning. The long flight range allowed them to stay in the air for a long time. The high accuracy of the targeting computer allowed them to strike targets exactly where needed, reducing the number of repeat passes. Years passed. The attack aircraft continued to serve, while other aircraft of its generation retired from carrier decks one by one. In the early 1980s, the aircraft took part in operations on the island of Grenada. The region was completely different, and the tasks were different, but the aircraft itself handled the new conditions just as confidently as it had a decade earlier. Now stop for a second and appreciate the time span. An aircraft that first took to the air in 1965 was still in service and performing combat missions nearly 20 years after its maiden flight. Many combat aircraft are retired long before reaching this age. Yet this attack aircraft, on the contrary, continued to prove its viability. The final major test for the aircraft was Operation Desert Storm in the early 1990s. By this point, the attack aircraft was over 25 years old, counting from its first flight. Imagine a car manufactured a quarter of a century ago that still goes out for a serious work shift every day and handles it no worse than new models. This was roughly the situation with this attack aircraft by the early 90s. 3 decades, 3 completely different regions, 3 different historical eras, and the exact same machine, which never once seriously let down those who flew it. But for any service, even the most reliable, an end must come sooner or later. And for this attack aircraft, it was a surprisingly quiet one. The year is 1993. A maintenance crew lines up on the deck of an aircraft carrier. The last attack aircraft of this type is preparing for its final flight with the US Navy. No loud ceremonies, no headlines in major publications, just another working day that became the last one for this aircraft. The engine starts for the last time under the flag of the United States Navy. The pilot taxis onto the runway as calmly as he has done hundreds of times before. Yet the journey began nearly 30 years ago. The first flight took place in 1965. Over these 3 decades, the aircraft went through several regions of combat operations, survived the transition of several generations of technology alongside it on the deck, and trained more than 1 generation of carrier pilots. In total, 1,569 of these machines were built. That is more than many far more famous combat aircraft of its time. And this is where a simple question should be asked. Why then do so few people know about this attack aircraft? Compare it with other aircraft of the same era. The high-speed SR-71 reconnaissance aircraft became a legend in its own lifetime, surrounded by rumors and secrets. The F-14 fighter achieved worldwide fame thanks to Hollywood movies. Another carrier-based attack aircraft, the A-6 Intruder, became a true cult classic among aviation enthusiasts. Meanwhile, this attack aircraft simply appeared, honestly did its job for decades, and then quietly left the stage. Perhaps that is exactly the point. The machine performed its tasks so reliably and without drama that there was simply no reason to talk about it loudly. There were no spectacular failures, there were no scandalous stories. There was just stable, quality work year after year. But the story did not end there. After being decommissioned from the US Navy, the aircraft did not head straight to museums or storage. It continued its service in the Portuguese Air Force. Imagine an experienced craftsman who retired from one job but continues to work in another place for several more years because his skills are still needed. This is roughly how the second life of this attack aircraft turned out. Portuguese pilots operated the aircraft until 1999. This means that a full 34 years after the very first flight of the prototype, this aircraft was still taking to the air and performing combat missions. For a machine initially designed as a temporary and inexpensive solution, this is a truly impressive service life. Today, when recalling the history of carrier aviation, other names are usually mentioned. Louder, more recognizable, more advertised in movies and the press. Yet this attack aircraft remains in the shadows. Undeservedly so if we evaluate its real contribution to the history of naval aviation, but perhaps quite naturally if we recall how exactly it served. It appeared without unnecessary noise, served without spectacular failures, and left the stage just as quietly as it had entered it nearly 30 years prior. And in this, perhaps, lies its main secret. Sometimes the best technology is not the one talked about the loudest, but the one you simply do not have to worry about.